Welcome back. So here we have an internal combustion engine, and now our job is to find the length of this connecting rod between this crankshaft and this blue piston here. And so here I can show it to you in slow motion. And so essentially we need to find the length between this red dot and then the middle of this blue piston. Of course, since we are learning about vectors, I want you to use vector concepts to find that length. And in order to do that, I need to give you some initial conditions. So essentially, what we need to do, we need to freeze this engine at some point and then give some initial conditions or initial dimensions to find the length of this connecting rod. And I'm going to do it like this. You have x in millimeters, y in millimeters. You have your blue piston here. Then this red dot on the crankshaft, it's here. And so this purple line, that's the connecting rod. And so the information that I'm going to give you is the following. This red dot, it circles like this. And so the center of the rotation, it's this point here. It's the origin of this coordinate frame. So you see you have this rotation circle, and the radius of this rotation circle is 1 to 5 millimeters. And so when I freeze this engine, then at the time when I freeze it, this angle here is 25 degrees. And then the horizontal distance from the center of the rotation till the center of this piston is 400 millimeters. So all these numbers here, they are in millimeters. And so, using this information, you have to find the length of this purple line. Let's call this point A, and let's call this point B. It turns out that there is an easy way to do it. Let's say that I have an XYZ coordinate frame. And in that frame, I have a point in space called P. I can represent the position of that point with a vector. I call this vector RP. This vector can be constructed with the three XYZ components, RPX, RPY, and RPZ. And this vector RP, it's called a position vector. It makes sense because it describes the position of something. The tail of that vector comes from the origin of the coordinate frame, and the head of that vector is where the point P is. But now let's define another point, and let's call it S. We draw another vector that goes from the origin of the coordinate frame till the point S. We call this vector RS. Again, we can construct this vector using three components. RSX, which is this arrow here, RSY, which is this arrow here, and RSZ, which is this vertical arrow here. So we can say that RP vector equals RPX times I plus RPY times J plus RPZ times K. And then RS vector equals RSX times I plus RSY times J plus RSZ times K. And finally, I will draw another vector from S to P, and I call it R, then P slash S. It means P with respect to S. So S is the origin for this particular vector, and P is where the vector is headed. That's why it's P with respect to S. This is one notation, which I will be using a lot. Another notation that you can use is this one, R and then SP, but without this slash sign. It would mean that you go from S to P, but with the slash sign, it means P with respect to S. If instead of going from S to P, I would go from P to S, so now the origin is P and now the vector is headed towards S, then instead of this notation, I would write rs slash p, so s with respect to p, or alternatively, I would write rps, so from p to s. However, in our case, we go from s to p. And now you can also say that rp vector equals rs vector plus rp slash s vector. It makes sense, right? I mean, that's how you add vectors. You put the tail of this purple vector where the head of rs is, and then you get rp, which is essentially your resultant vector. But then you can also say that rp with respect to s equals rp minus rs. It means that this vector here, it's really the difference of these two vectors. It's the difference of rp and rs. And so if we now use the I, j, and k components, then rp slash s equals, this is the rp vector minus, this is the rs vector, and so all that equals I times rpx minus rsx plus j times rpy minus rsy plus k times rpz minus rsz. And so this vector here, it's called a displacement vector. So the difference of two position vectors is a displacement vector. It's different from distance though. Distance is a scalar quantity. It just tells you how long something is. It has no direction. But displacement is a vector. It has a direction. In our case, its direction is from point S to point P. If you divide the displacement vector magnitude by the change of time, or delta t, then you get the average velocity vector magnitude. So delta t is the time that you need to go from S to P. So if here you are at t0 and here you are at t1, then delta t would be t1 minus t0. And the average velocity vector that you get has the same direction like the displacement vector. So velocity is a vector. But remember, velocity does not equal speed. Speed is a scalar quantity and velocity is a vector quantity. Speed simply shows you how fast you cover distance, which is also a scalar. So distance over delta t equals average speed. And the reason why I say that speed and velocity are average is because I'm not assuming that this delta t is infinitesimally small. Maybe it takes you 40 seconds to go from S to P. During that time, your speed might vary. Sometimes you might go faster, sometimes you might go slower. So that's why I say average velocity and average speed. But okay, let's go back to our displacement vector. By taking the difference of rp and rs, you have essentially created a new coordinate frame. The origin of this new coordinate frame is this S point. And here you also have three axes, x apostrophe, y apostrophe, and z apostrophe. Note that x apostrophe is parallel to x, y apostrophe is parallel to y, and z apostrophe is parallel to z. You haven't rotated this new frame with respect to the old one in any way. You have simply shifted the coordinate frame in such a way that the origin of it is now where the point S is. And from that new origin, I draw my displacement vector, rp slash s. And so from this new coordinate frame, we can construct this displacement vector like this. This component here, that's in the x apostrophe direction, and it's this one here, rpx minus rsx. Then this component, that's in the y apostrophe direction, and it's this one here, rpy minus rsy. And then this component that goes vertically down, that's in the z apostrophe direction, and its magnitude is this one, rpz minus rsz. So this x component has a positive x apostrophe direction, this y component has a positive y apostrophe direction, and then this z component that you have here, that's in the negative z apostrophe direction. Note that if instead of rp minus rs, I had rs vector minus rp vector, so I would have rs with respect to p, then my new coordinate frame would have been shifted here. Its origin would be the point P, but again, x apostrophe, y apostrophe, and z apostrophe, they would be in the x, y, and z direction. So by taking this difference, you only shift coordinate frames, you don't change their orientation. And so your displacement vector would be this one then, your rs slash p, and then your x apostrophe component, it would be this one, then your y apostrophe component would be this one here, and z apostrophe component, it would be here pointing up. Note that all these three components, they have the opposite directions to what you had here. So if here you had rpx minus rsx, then here you would have rsx minus rpx. It would be this one here. Then here you have rpz minus rsz. Then here you would have rsz minus rpz. And then here you had rpy minus rsy. Here you have rsy minus rpy, which is this one here. So all the components of the displacement vector from the new coordinate frame would have the same magnitudes, but they would be opposite in direction. And it makes sense because now you don't have rp minus rs. You have rs minus rp. However, our case was rp minus rs. This was our case. So let's stick with that. And now what you can do, you can take your displacement vector and you can calculate its magnitude. So the magnitude of your displacement vector, or I will simply write it like this, it equals rpx minus rsx squared plus rpy minus rsy squared plus rpz minus rsz squared, and then I'm going to take all that to the power of 1/2, which is essentially taking the square root of everything here. And so this magnitude here, it will give you the length of this displacement vector arrow. In other words, it will give you this straight line distance from point S to point P. And using this concept of finding the length of your displacement vector, using that, you can solve this engine exercise. Now you can calculate the length of this connecting rod knowing the initial data that you have here. So try it out by yourself first, challenge yourself, try to calculate the length of this connecting rod using this concept here that we have just discussed, and then see my solutions in the next video. Thank you very much. Welcome back. So let's now calculate the length of this connecting rod using the vector principles that we discussed in the previous videos. We know that the center of rotation of this point A is here in the origin of this coordinate frame. So let's call this origin O. And so how about I define a position vector from the origin till A, and I call this position vector A with respect to O, or simply A, and you know that the magnitude of this position vector is 125 millimeters, and you have this angle here, 25 degrees, so you would agree that the x component of this position vector would be the following: minus 125 times sine 25 degrees times I. It's minus because it points in the negative x direction. And then you will have plus 125 times cosine 25 degrees times j. It's positive because it points in the positive y direction. And then to be complete, I could also write plus 0 times k. Since we have a two-dimensional problem right now, we don't have a third dimension, which means that you have 0 millimeters in the k direction. But if you had a three-dimensional problem, then you would have another number here. And then we can define another position vector, this one here, and we can call it RB with respect to O, or simply RB. And so it would be 400 times I plus 0j plus 0k. And of course, both position vectors are in millimeters. And now what happens if I write RB minus RA? Well, you will get a displacement vector, RB with respect to A. So your displacement vector would start from point A and it will go till point B along your connecting rod. So RB with respect to A equals I times 400 minus 125 times sine 25 degrees, then plus j times 0 minus 125 times cosine 25 degrees, and plus k times 0 minus 0. So your displacement vector equals 452.8 I minus 113 times j plus 0k. So essentially, like we discussed before, by taking this difference, you have shifted your coordinate frame. This one here, that's your x apostrophe. Then this one here, that's your y apostrophe. You can see that you have only shifted this coordinate frame. You haven't rotated it. X apostrophe still points in the x direction. Y apostrophe still points in the y direction. And so this component from here, from the origin of this new coordinate frame, it's this one here, 452.8 millimeters. And then this component here that points down, it's this one, minus 113 millimeters. So it's this component here. It points in the negative y apostrophe direction. And well, at the moment we don't have to worry about our third dimension. But again, if you had a three-dimensional problem, then instead of these zeros, you would have other numbers. That's why I'm including this third dimension in order to give you a structure for a general three-dimensional problem. And so the magnitude of this displacement vector is 452.8 squared plus 113 squared plus 0 squared, and you take the square root of it, and you will get 467 millimeters. And there you go. The length of your connecting rod is 467 millimeters. So when you go from this red point till the middle of this piston, then this connecting rod, its length is 467 millimeters. And as you can see, it was very easy to find using these vector concepts. Thank you very much. Welcome back. I have a tower here. We assume that there is no wind. There are 3 cables here that are pre-tensioned. The tension force in the cable that connects the tip of the tower, D, and this point A, it's 400 newtons. Then the tension force in the cable that connects point D and this point C, that's 600 newtons. And then the tension force in the cable that connects D and this one, point B, that's 800 newtons. And so my XYZ coordinate frame is here, and the origin of this coordinate frame is right here, where this tower starts. I'm going to call this origin O, and so all these cables, they touch the ground on this xy plane. And here you can see where the points A, B, and C are located on the xy plane. And so now, our job is to find the magnitude of the resultant force from these three forces in the point D. So we are analyzing this one, the tip of the tower. And then we also need to find the coordinate direction angles of this resultant force. And we have to find it with respect to this point D. So you have your point D, you have some kind of FR. This is the new coordinate frame whose origin is in point D. And then you have to find your alpha, beta, and gamma. So that's what we need to do. You almost have all the tools to solve this problem. But there is one more thing that I want to mention before I let you solve it by yourself. Do you remember the general unit vector u? And do you remember that your force vector could be written like this: the magnitude of the force vector times the general unit vector, and that gave you this expression here. And so to solve this problem, you obviously need u vectors for these three forces that you have here in the cables. You need to have a general unit vector in this direction from D, then in this direction from D, and then in this direction from D. It makes sense because, for example, if we take this force from D till C, 600 newtons, this 600 newtons, that's this one here. That's your magnitude. However, what you would like to have, you would like to have this one. In other words, you would like to have this form from point D. Remember, we have this new coordinate frame, and this point here, that's D. Right now, this I vector here, it's this one here, then this J vector here, it's this one here, and then this K vector here, it's this one here. And so you need this general unit vector for this force here so that you could go from 600 newtons, which is the magnitude of the force, to this format where your 600 newtons is decomposed into three components. And why do you want to do that? You want to do that because once you have decomposed these three forces into its x, y, and z components with respect to D, you can very easily add them up in 3 dimensions. Remember, when you work in 3D, when you want to add vectors, you should always decompose them into its I, j, and k components. And so here we took this force, 600 newtons, as an example, but the same logic applies here with 400 newtons and 800 newtons. So for each force, you have to generate this general unit vector. So how do you do that? Well, do you remember that when you had a random vector A, then you could get the general unit vector u that points in the A direction and whose magnitude is 1, you could get it like this. U sub A vector equals ax over A times I, ay over A times j, plus az over A times k. This was the magnitude of your A vector, this was the x component, this is the y component, and this is the z component. It turns out that when you know the dimensions of your structure, then it's very easy to generate these general unit vectors. Suppose that you want to have a unit vector A with respect to D. So it's this one here. You go from point D to point A. And you want that because one of your forces goes from D to A. And you want this unit vector in the direction of that force vector. And so, first of all, I will simply have the position vector of this point D with respect to this main coordinate frame, with respect to this origin here. So my position vector d with respect to O, so with respect to this point here, or simply rd, well, that would be 0 times I plus 0 times j plus 24 times k meters. And you can see that this is the case because the length of the tower is 24 meters. And from the origin, it only goes up along the positive z-axis. And now I create another position vector with respect to this origin, RA with respect to O, or simply RA. Well, that's 15I plus 20j plus 0k meters. Again, it makes sense because point A is on the xy plane. It does not go up nor down along the z dimension. And now if I write RA minus RD, then I will get RA with respect to D. And that will be I times 15 minus 0 plus j times 20 minus 0 plus k times 0 minus 24 meters. So RA with respect to D equals 15I plus 20j minus 24k meters. So remember, these i's here that we have, and these j's and these k's, they are these ones here. This is I, this is j, and this is k, because you're measuring those vectors with respect to O. But now this I and this j and this k, it's this one, I, j, and then k, with respect to this shifted coordinate frame, which is located here in point D. And so this RA with respect to D, it's this displacement vector here that goes from D till A. Just to make it clear, this is the tower from the origin, this is position vector RD, this is point D here, this is point A here, this vector here, that's RA, and then this vector here, that's RA with respect to D. And now if you take the magnitude of RA with respect to D, which is 15 squared plus 20 squared plus 24 squared, which is 34.7 meters, then that gives you the length of this cable from D till A. That's very cool, but we don't actually need the length of this cable. We need a unit vector from point D in the direction of A. We need this one here. But now, we will use this formula. But instead of A vector, we have our displacement vector. And instead of magnitude of A, we have the magnitude of our displacement vector. And so I can write that U, A with respect to D, is this displacement vector, A with respect to D, divided the magnitude of this displacement vector. In other words, I have 15 over 34.7 times I plus 20 over 34.7 times j plus minus 24 over 34.7 times k. Now for each component, the magnitude is in meters and that component is in meters. That's for the I component, j component, and k component. So in the end, your units for this general unit vector will be meters over meters, which means that a unit vector is a dimensionless vector. And so now when you calculate the ratios of the components of this unit vector, then you will have UA with respect to D equals 0.432I plus 0.576J minus 0.692K. if you take the magnitude of UA with respect to D, you will get 1. And now you can use this unit vector to decompose this force of 400 newtons that goes from D till A. So the force A with respect to D is 400 newtons, but I can also write it down in this form. The magnitude of that force times the unit vector, which is in the same direction. So I will have 400 times, and then this unit vector here. And so that means that FA with respect to D equals 172.8 I plus 230.4 J minus 276.8 K. And that's already in newtons. And there you go. This is how you decompose a vector into its x, y, and z dimensions by taking advantage of the dimensions of your structure. Again, you had a force vector that goes from point D till point A. You know its magnitude, which is 400 newtons, but you don't know its separate x, y, and z components with respect to point D. But you know the dimensions of the structure. So through two position vectors, one from O till D and the other one from O till A, you obtain this displacement vector that goes from D till A. Then you calculate its magnitude, and even though by itself this displacement vector has nothing to do with this force vector, but it points in the same direction, which means that if you take the magnitude of this displacement vector, then you can compute the general unit vector in the same direction. And then you can use this general unit vector that also points in the same direction like this force vector. You can use it to decompose your force vector. So using physical dimensions, you obtain the unit vector, and then you use it to decompose your force vector. And so we have done it for one force. Now you have to do it for two other forces, and then you have to obtain your FR vector with respect to D, and you have to find alpha, beta, and gamma from this shifted coordinate frame. So try it out by yourself first, and then I'll do the solutions in the next video. Thank you very much. Welcome back. So let's now solve this tower exercise. In the last video, we already decomposed this force vector A with respect to D. Approximately it looked like this. And now we have to decompose the force vector B with respect to D, and then C with respect to D. And once we have that, then we can compute our resultant vector with respect to D. And so let's decompose this force vector that goes from D till B. Again, I'm going to start with my position vector with respect to origin until the point D. That's 0 times I plus 0 times j plus 24 times k. Then I will obtain the position vector from the origin till point B. That's minus 6 times I plus 4 times j plus 0k. And in fact, in order to later decompose this force vector, C with respect to D, let me also obtain this position vector, RC, with respect to this origin. That's 16I minus 18j plus 0k. Then let me right away obtain the displacement vector, B with respect to D. That's RB minus RD. That's this one. It makes sense, right? You go 6 meters in the negative x apostrophe direction, then 4 meters in the positive y apostrophe direction, and then 24 meters in the negative z apostrophe direction. And that's how you end up in point B. That's your path from D till B. First of all, you go 6 meters in this direction, then 4 meters in this direction, and then 24 meters in this direction. Then we can also right away compute the displacement vector of c with respect to d. That's rc minus rd. It's 16I minus 18j minus 24k meters. Again, you go 16 meters in this direction, 18 meters in this direction, and 24 meters in this direction. First parallel to x apostrophe in the positive direction, then parallel to y apostrophe in the negative direction, and parallel to z apostrophe in the negative direction as well. Then the magnitude of RB with respect to D, that's 25.1 meters, and the magnitude of RC with respect to D, that's 34 meters. You just use the 3D Pythagoras theorem for that. This one is for RBD magnitude, and this one is for RCD magnitude. And so once you have them, it's very easy to compute the general unit vectors from D in the B direction and in the C direction. This is in the B direction from D, and this is in the C direction from D. And so now we can calculate FB with respect to D. We know its magnitude, which is 800 newtons. Then we multiply it by the unit vector, which is this one here. Again, this one, it's 800 newtons. And so this is your decomposed force vector, B with respect to D. And then I'm going to do the same thing with FC with respect to D. I have its magnitude, which is 600 newtons, times the unit vector, C with respect to D. So it's this one here. And so that's your answer. So this force vector, C with respect to D, its magnitude is 600 newtons. But with respect to this point D, I have 282 newtons in this direction, 318 newtons in this direction, and then 424 newtons in this direction. And so from the origin at point D up until this point, this vector is 600 newtons. So that's the logic of it. And so I will also write it here. This is FB with respect to D. This is FC with respect to D. Of course, they're all in newtons. And now you need to calculate your resultant vector with respect to D. But since all your three forces are decomposed into their x, y, and z components, this calculation will be very easy, especially since we assume that there is no wind, which means that there is no external aerodynamic force that comes from wind. So we assume that it doesn't exist. And so the resultant force equals Fa with respect to D plus Fb with respect to D plus Fc with respect to D. So you just need to add up the I components, then the J components, and the K components. And if you do that, then this is what you will get. This is for the I component, this is for the J component, and this is for the K component. The magnitude of the resultant vector with respect to D is the following: 264 squared plus 40 squared plus 1466 squared. You take the square root of it and you get 1490 newtons. And finally, to calculate alpha, beta, and gamma for the resultant vector, you know the formulas for that as well. Cosine alpha r, so it's alpha for the resultant vector, that's 264 over 1490. Then cosine beta r, that's 40 over 1490. And then cosine gamma r, that's minus 1466 over 1490. So alpha r equals 79.8 degrees if you take the inverse cosine of this ratio. Then beta r equals 88.5 degrees. And then gamma r equals 170 degrees. And there you go, that's how you do it. This is your shifted coordinate frame here. This origin that's the tip of your tower, that's this D point. This component, that's 264 newtons. Then this component, that's 40 newtons, which is this one, in the positive y apostrophe direction. And then this one, that's minus 1466 newtons in the negative z apostrophe direction. Of course, in reality, this arrow is a lot longer. It's just I'm simply out of space. And so, this red vector, it goes from the origin till this tip. That's my FR. So it's here. And now, from the positive x apostrophe axis, I define alpha r. From the positive y apostrophe axis, I define beta r. And from the positive z apostrophe axis, I define gamma r. So this is just to give you an idea visually of what you have been trying to find here. But now we are not done with this tower exercise. Now I have another question for you. Now I want my cables to be pre-tensioned in such a way that the resulting force Fr points down along the tower. So I want my Fr to point parallel to this z-axis only. Now the magnitude of Fr stays the same, 1490 newtons. That will not change. This is what you found here. But I want this force vector to go down along the tower. And another information that I will give you is that each cable that you see in this image is only able to withstand 900 newtons of tension force, which means that this cable here, from D till A, so the magnitude of Fa with respect to D, maximum that it can be, it's 900 newtons. Also, the maximum of force B with respect to D, that's also 900 newtons. And the maximum of force C with respect to D, that's also 900 newtons. Meaning that if the tensile force in those cables is greater than 900 newtons, then the cables will break. And so knowing this information, and knowing that your resultant force now needs to have the same magnitude, but it has to point down along the tower, is it possible? Will the cables be able to withstand the forces necessary in order to fulfill this requirement, that the magnitude of Fr is 1490 newtons, and it has to point down along the tower? So try to figure that out by yourself, and then I'll show you the solution in the next video. Thank you very much. Welcome back. So let's now solve this other problem that I gave you in the end of the previous video. So the challenge was that the forces that the cables exert on this point D, in the end, the resultant force that you get from them, it had to point down along the tower, and the magnitude of Fr was still 1490 newtons, but it only had to point down along the tower. And then another piece of information that we had was that each cable was only able to withstand 900 newtons, not more. If the tensile force is more than 900 newtons in either of those three cables, then the cable will break. And so, knowing that, is it possible to have a resultant force with this magnitude, but when it only points down along the tower? So let's first of all figure out what our Fr needs to be. This here is my shifted coordinate frame. This point is D, it's the tip of the tower, and so essentially I want this to be my Fr, which is 1490 newtons, which means that in terms of unit vectors, Fr equals 0I plus 0J minus 1490K. That's of course with respect to this D. Also note that you have 90 degrees here between this x apostrophe and this FR vector, and here between y apostrophe and FR vector. That means if I define an angle from the positive x apostrophe axis, alpha r, that's 90 degrees. Also, the beta angle from the positive y-axis, beta r, that's also 90 degrees. And then from the positive z apostrophe axis, I have gamma r, and that's 180 degrees. You can also see it mathematically. Alpha r equals inverse cosine, and then you have 0 divided by the magnitude of the vector. That will give you 90 degrees. Similarly, here you also have inverse cosine, and then 0 divided by 1490. That also gives you 90 degrees. And then for gamma r, you have inverse cosine, and then you have minus 1490 over 1490. And that, of course, will give you minus 1. And inverse cosine minus 1, that's 180 degrees. And so how did we get our resultant vector in the first place? Well, we added up these three vectors, right? You had force A with respect to D, plus force B with respect to D, plus force C with respect to D, and you got your FR with respect to D. Now, obviously, we don't know what these three forces are. We have to find them. First of all, force A with respect to D, I can write it out in this way. This is the x component, y component, and then the z component. Similarly, this is how I can write out FB with respect to D, and this is FC with respect to D. And so if I add up my I components, then I need to get 0I. If I add up my j components, I need to get 0j. If I add up these components, I need to get minus 1490k. Why? Well, that's because if I add up these three vectors, then I need to get this vector. And this vector equals 0i plus 0j minus 1490k. That's my resultant vector. So essentially, we have three equations here. We have equation 1, equation 2, and then equation 3. So right now you should think vertically. So one equation will be FA slash dx plus FB slash dx plus FC slash dx equals 0. That would be equation 1. And then similarly you have equation 2 and equation 3. But you have 9 unknowns here. 3 equations, but 9 unknowns. That's not a good sign, because if you have only 3 equations, but 9 unknowns, then you cannot find those 9 unknowns. However, if you remember, then you had 3 general unit vectors. UA with respect to D, UB with respect to D, and UC with respect to D. And thanks to these 3 unit vectors, I can write my force A with respect to D like this. The magnitude of that vector times UA with respect to D. Similarly, I have force B with respect to D. I have its magnitude times the unit vector B with respect to D. And then force C with respect to D. Again, magnitude times UC with respect to D. We calculated these unit vectors in the previous videos. UA with respect to D was this one here, and then UB with respect to D was this one, and UC with respect to D was this one. And so thanks to that, we can rewrite these 3 vectors like this. This is vector FA with respect to D, this is vector FB with respect to D, and this is vector FC with respect to D. Note that these three vectors, they are the same vectors that you have here. But now, for example, this component here, that's this one here, fa/d x. And then, for example, this one here, that's this one here. And for example, this one here, that's this one here, and etc. Note what I have done. I have rewritten all these components in terms of vector magnitudes and the unit vector components. And now if in this equation, this one, and this one were different, then now you have the vector magnitude here, here, and here. So here you had 3 unknowns, and here you have 1 unknown. And that's very good, because if I now add the I components, the j components, and the k components, then here I will need to have 0i, here 0j, and minus 1490k, because this is what your resultant force vector is. Then now you still have 3 equations. This is equation 1, this is equation 2 that you have here, and this is equation 3 that you have here. But now you also have 3 unknowns, because these unknowns are the same, these unknowns are the same, and these unknowns are the same. Now your unknowns are your vector magnitudes. And now, let's take these 3 equations and write them down like this. First of all, for the I component, I have this equation here. That's this vertical equation 1 here. Now I have simply rewritten it in a horizontal way. Then for the j component, I have this equation. Again, it's just equation 2, which is written vertically here, but here it's written horizontally. And then for the k component, I have this equation here. Again, it's this equation 3. Now it's written horizontally. And now we have to find our 3 unknowns, fa/d, fb/d, and fc/d. For that, I'm going to write these 3 equations in the matrix vector form. In this vector, I'm going to put my 3 force magnitudes. Then all these numbers, they will go inside this matrix. And then here I will have 0, 0, and minus 1490. So let this matrix be A, let this vector be x arrow, and let this vector be b arrow. And so you have this form, A matrix times this unknown vector that you have to find, and then this b vector. And how do you find this x vector? Well, you simply take the inverse of this A matrix and you put it on both sides of the equation. Now this one here, this will be an identity matrix. An identity matrix times the x vector equals that x vector. An identity matrix, it's like 1. If you multiply something by 1, you get that something. And so you have x vector equals inverse of A times the b vector. Now, in order to find the inverse of a matrix, you can either use the techniques from linear algebra, or you can do what I do. I usually just go on Google, and then I write something like inverse matrix calculator, and then you will find some kind of web page in which you can insert your 3x3 matrix, and then it will give you this inverse matrix back. Or you can also do it in Python or MATLAB. Since this course is not about linear algebra, I recommend you to just use some readily available tools to find the inverse matrices fast. And so if I now take this formula, then I will write it down like this. So these are my 3 unknown variables. And so this matrix here, that's your A inverse. This is your x arrow, this is your A inverse, and this is your B vector. And if you multiply A inverse by this B vector, then you will get here 117, 1129, and 466, and all of them are in newtons. So this magnitude is this one, this magnitude is this one, and this magnitude is this one here. So you have found three vectors that will give you this resultant vector. And so now that we have the answers for our force magnitudes, we can see if all our cables are able to cope with those forces. The maximum tensile force that you could have in a cable was 900 newtons. So Fa/d equals 117 newtons. That's less than 900 newtons. So that's okay. Then Fb with respect to d, that's 1129 newtons, which is greater than 900 newtons. And that is not okay. And then Fc with respect to d, that's 466 newtons, and it's less than 900 newtons. So that's okay. But in general, the situation is not okay. Because if this is the force resultant vector that you want, then with the cables that you have currently, this cable that goes from D to B, it will break. So either you have to lower your expectations, or you need to get stronger cables. Or another option would be to place this B somewhere else on this XY plane, because your force also depends on the location of this point B. And now I want to mention one more thing. The forces that we found here, they are all positive forces. So let's say that this is the tip of the tower, this point is D, and so the cables exerted three force vectors on this point D. Fb with respect to D, Fa with respect to D, and then Fc with respect to D. Now, because of Newton's third law, if I disconnect this cable from point D and from point B on the ground, and I do it with this cable as well, that is connected to point A on the ground, and the same thing here, the one that is connected to point C on the ground, if I mentally disconnect them, not in reality, but if I mentally disconnect them, then due to Newton's third law, this cable will experience the same force but in the opposite direction in here, and the same force Fb/d would be in this direction here, and then this point B, it would feel this force in this direction. And the same thing with this cable. These are your forces. And the same thing here, these would be your forces. That's due to Newton's third law. Since these cables are not moving anywhere, then if point D experiences this force in this direction, then in the same location, this side of the cable that is connected to point D experiences the same force with the same magnitude but opposite in direction. And now from this drawing, you can clearly see that all your cables are in tension. So this is cable A, cable B, and cable C, and they are all in tension. The force analysis that we made here, they were about point D. And so these forces here, they were with respect to this point D. And so since they are positive, point D experiences these three forces outwards. And from this drawing you see that that automatically makes cables experience tensile forces. However, what if one of the forces here became negative? Let's say this Fa with respect to D. What if instead of 117 newtons, I had Fa with respect to D minus 117 newtons? Well, that would mean that instead of this arrow here, I would have this arrow here. And so according to the Newton's third law, which is action and reaction, on this side of the cable, you would have this force. And then on this side of the cable, you would have this force. And then point A on the ground, it would experience this force. And now if you look at cable A, then you can see that it does not experience tensile forces anymore. It experiences compression forces. It is being compressed. But unlike rigid beams that are made of solid material, cables cannot take compression load. They simply become like this. And so if in your force analysis here, you had ended up with a negative force, then it would have been pretty bad. That cable A, it would be in compression, and that could make the tower unstable. So for example, if an external force, for example, force from wind, causes one of the cables become in compression, that could make the tower unstable. Or the other two cables might break because of that, because if this cable is in compression, then it's useless. It's not helping support the structure. And that means that the other two cables have to support the entire structure, even though it was designed that 3 cables would support this structure. But if one of the cables is in compression, then 2 cables need to do it. And then in other 2 cables, cable B and C, the tensile forces might become too big and they might break. And so in general, when you work with these kind of problems, then this is the convention. This is your cable. Then if the cable is in tension, then forces are positive. And if the cable is in compression, then the forces are negative. Which means that in this connection point D, if your cable is in tension, then from the point of view of point D, a positive force is outwards. And if the cable is in compression, then in this connection point, from the point of view of point D, the force is inwards. And that means that this force is negative. So this force here, it would be negative, and then this force here would be positive, and also this force here would be positive. But like I said, when you're stabilizing a structure with cables, then you should always avoid these kind of situations where your cable becomes in compression. A cable in compression contributes to nothing, and quite frankly, it's dangerous. So always make sure that your cables are in tension. Thank you very much.